part of the geospatial team. I'm part of what we call the MVAM team. For those that are familiar with VAM work, M stands for mobile, so it's everything that has to do with what we call remote monitoring of food security. And by remote, we mostly mean with cell phones. So my team, for example, does a lot of remote surveys, calling people, calling households to try to know the food security situation. Not doing a face-to-face survey, but doing a little phone call. I'm not going to talk about that. I'm going to talk about applications of artificial intelligence and two projects that are very linked with the work of Sarah and the remote sensing team in general. The first project I'm going to present, we call it Humanitarian High Resolution Mapping. It's trying to link the food security assessment data, the survey data, the face-to-face survey data in particular, with the remote sensing world. So when we do surveys, we usually collect GPS coordinates, and by looking at satellite images and other remote sensing or geospatial layers, we can extract information that are not in the survey and that can bring more information to the survey. But before I go into the details of the model, you have to, let's go back a bit to what is a survey and what is an assessment in particular, what we call a food security assessment, and what the results look like in general. So I don't know how familiar we are with WFP assessment. This is a map of Tanzania, an assessment that's called, I think, a CFSVF, or Comprehensive Food Security Assessment. Data was collected, I think, in 2010. That's an old survey. And the colors here show the food insecurity in Tanzania at that time for a specific indicator. I think the indicator here is the proportion of poor and borderline food consumption. So I'm sorry, there's no legend, but yeah, if you have to make decisions, if you're part of program, if you're part of the government, and you want to make decisions on where to prioritize your assistance to vulnerable population, you'll usually look at assessment results. So a big report, look at maps, and you'll see here it's darker red. So maybe I need to send more food assistance than here, which is white color. But the problem here is that this is an admin one level, so it's a regional level. So if here you have to send assistance, well, that's a big place. So you don't know exactly what villages are in need of assistance here. You don't know what's the population of these villages, for example. Another example is here. It's a light red, so there is some problem, but not as much as here. But this is on average. So maybe here, in fact, there is some very vulnerable population in some part, and in the other part, you have some populations that are doing very well. So on average, it's doing okay. But if you need to send food assistance, you might want to know that there are some very vulnerable populations somewhere here. So this project that we started a year ago with some colleagues, with help from the different teams in VAM, is about taking these big results maps at a high level and downscaling them at a higher resolution. So we're not the first one in VAM to do this. There have been some work in Asia involving WFP with techniques called small area estimates. Has anyone heard of small area estimates?
Yes.
Okay, so for those that know for small area estimates, the idea is similar. It's downscaling survey results, but I'm not an expert, but I think they use census data to do this, to create a model, because census data is much more granular, you have much more data, compared to an assessment that is representative at admin1. So you create a statistical model that looks at the relationship with the census data to make low-level predictions, high-resolution predictions. Other approaches, more recently, in the last, I would say, 5 years in academia, is to use remote sensing covariates to learn relationships with your survey data. So this paper was published in the Science in 2016, and they look at satellite images, very high resolution satellite images. So typically the ones you have on Google when you zoom a lot, or the providers, or GTAC Globe or Planet. We talked a lot about it in the workshop, and they try to extract some relevant features to predict poverty here. So it's not food security, it's poverty, and they use poverty as defined by DHS in the DHS surveys. So I don't know if you're familiar also with DHS surveys, big surveys that are often conducted every couple of years in sub-Saharan Africa and in other places. So how does it work? So yeah, a household survey. A household survey, it's not a random sampling of a country. It's not a random spatial sampling. You don't go everywhere. You don't send enumerators everywhere on the field. You send them to what we call cluster or enumeration areas. So you randomly select some enumeration area, some clusters, so that corresponds to more or less villages in rural settings. And within each village, you ask them again to sample, to select randomly 10 to 20 to 30 households, and you interview these households. And that's how you collect survey data usually. It's called two-stage cluster sampling. So when you do this face-to-face survey, usually nowadays you do it with tablets. So I don't know if you're familiar, but there's a software called ODK. There's many other softwares that are built on top of ODK, where you do the survey with tablets. And a nice feature of these tablets is that you can automatically collect the GPS coordinates of where you do the household survey. So when we analyze the data, we can plot the GPS coordinates of the survey. So this is a survey that was collected in Mali with WFP and its partners in February of this year. And in black, I plotted the cluster location, so the village location of where this survey has been collected. And if I zoom in, so if I zoom in a city, around the black point, I would see 10 red points. So 10 households have been surveyed in each cluster. So a cluster, I said, it's a village, but in the urban area, it corresponds to a neighborhood. So you can see that we don't go everywhere. We only go to specific neighborhoods, and within specific neighborhoods, the cluster, we interview 10 people here. It can be 20 in other survey settings, but here it's 10 people. Another cluster, 10 people. And you have cluster a bit everywhere that follows more or less the population distribution in one country. So if I zoom on a specific cluster, on two specific clusters here in Mali, in two different locations, by looking at these satellite images, can you guess which of this image, on which of this image the food security situation, or if I want to put it in other terms, if we look at the poverty situation, is the better? In which place you think people have a better poverty status or better off? Can you guess from the satellite images? Do you have any ideas? Left or right? Left? Left people are more richer. Why? Why do you think?
Because they have better infrastructure. You can see the roads.
Okay, you can see the roads. What else can you see?
The living standards are more better than the right one.
What, sorry?
The living standards.
Yeah, okay.
And better access to public services.
So better, you can already see here better access to public services. It's a bit, yeah, it's a bit tricky, but maybe you can see some bigger buildings that maybe are schools or whatever, and think better access.
Electricity,
You can see
water,
electricity.
Probably they will have more food on the right side.
More food on the right side.
Yeah.
So, okay, there is another thing that maybe because here you don't see any crops, but on the right side you see some agriculture. So
And few houses.
they have some agriculture production maybe. But yeah, it depends how you measure poverty or food security. But as you said, there is many things you can grab from the eye. Other images, again in Mali, 2 different locations. What do you think? Left or right here? Left also. So you already said a lot of things. You can see roads, you can see buildings, the roof type. You can see that better roof type. Well, better. It's relative, but you can see water here, and you can see some vegetation that you don't see here. So that's the intuition behind behind what behind this project is. Well, from satellite images, just looking at with your eye, we can already make an estimation of the poverty level of a place. So we don't want an analyst to look at thousands of images of a country because this is very high resolution. So if you want to cover a whole country, you will have to look at thousands of images and make a guess. We want to do this in an automatic way. So we want to extract features here from satellite images that link with the poverty or the food security situation of the inhabited place. So to do this, we do what we call transfer learning. So that approach was introduced in the paper I showed before from Science. It's based on what we call neural networks. So neural networks is a type of machine learning algorithms that are very popular these days in computer vision. Computer vision is recognizing images. So, for example, on your smartphone, when you take a photo, often, or on a camera, often you will have a bounding box around the faces of people. So usually that's a neural network behind. That's analyzing the picture on the image, and that knows how to recognize faces based on features it extracts from the image. We tried the same approach, but not to recognize faces, to recognize luminosity at night. So luminosity at night. Why luminosity at night? Because it's a good proxy of poverty, meaning that if there is no night lights, it's a poor place, and it's a lot of night lights. Usually it's a more healthier place with more infrastructures, etc. So we train a network to recognize from satellite images that are free band satellite images, so red, green, blue bands, like the usual visual things that you can see, to recognize if there is some night lights and what's the intensity of night light there is. And we train a network to do that, a neural network. And rather than taking the output predictions of a neural network, so the output predictions would be what's the intensity of night lights, we go back into the neural network and we extract some features that are in the middle. It's a bit complicated, but we use these networks as a proxy of poverty, because night lights can be a proxy of poverty, and we extract features that don't mean anything. It's numbers. So it's like if I have to recognize a face, for example, on an images, I know that before saying there is a face or there is not a face, there is some numbers in the neural network that indicate well if there is a face, and these these things can be, or maybe you recognize an eye, maybe you recognize a nose, maybe you recognize some strange things, but it's in between. And that's what we do here. We don't look at night lights, we look at what's before night light. So maybe it's recognizing roads, maybe it looks at vegetation and things you can see on the images, but we don't know exactly. That's a bit abstract features we extract. So we get a lot of abstract features from these high resolution satellite images. But that's not the only thing we take for this model. We also look at the distance to infrastructures, and in particular schools and hospitals. So now it's the same images, but I tell you that the closest school is 300 meters, the closest hospital is 800 meters. On the right side, it's 1 kilometer and 4 kilometers. What does it tell you? You have more information now. Like if I want to estimate the poverty situation of left and right, the fact that you know that hospitals and schools are closer to here. It's another information that we can add to the model. And this information, we don't get it directly from the satellite images. It's true that someone said you can recognize some infrastructures maybe, but we're not at that stage yet of recognizing schools from satellite images. We take them from OpenStreetMap. Everybody is familiar with OpenStreetMap? Okay, so OpenStreetMap, not everywhere, but more and more in sub-Saharan Africa, at least where we've tried these, schools and hospitals are quite well mapped. So we have volunteers that have been mapped the location of schools and hospitals and many other things, and that you can extract for free. It's open data. So we extract this from the OpenStreetMap database, and we calculate for each location in a country where we want to make predictions. We extract the distance to school and hospitals and other things that we have tried also. So
what was the benchmark for measuring this distance?
What do you mean the benchmark?
From big
we take images of 1 kilometer by 1 kilometer. We take the center of it, and we look at the distance from the center of the image to the school or hospital. So that's and we can also. It takes more time to run, but we can do it with smaller images and smaller images. So same thing here. Again, night lights. So before I explained how we use night lights as a proxy of poverty to train a neural network, but we also extract the raw night light value as a feature of the model. So the two images were taken from the same area, but two different places. So we can see that it's more an urban zone, so you have more night lights here. The green is the intensity of night lights, and here you have almost no night lights. So we extract also this information as a feature. Other thing we do is we look at the remote sensing indices. So that was presented this morning. You were introduced, and a lot of you know already what is NDVI. So we look at the NDVI index over a period of 1 year at all the locations we want to predict poverty. We also look at the water index and the built-up index to know what's the intensity of built-up in the location. So we put that also as features in the model. And when we have all these features together, we train this time a linear model, so a classic linear model, to learn what's the relationship between all those features and the indicator we want to map at high resolution. So if it's poverty, we create we train a linear model with features and poverty. If it's food security, it can be the FCS, it can be other indicators that you're familiar with. So to recap a bit, from OpenStreetMap, we look at the infrastructures, schools, hospitals, and we compute the distance to these infrastructures. From Google Maps API, we use very high resolution images, so 1 meter pixel resolution. It's a free bands picture, RGB. we put this image into the neural networks, and we extract some neural network features that are black box features that correlate well with poverty. From Sentinel-2 images, we do the same. We also put them in the neural networks because they give you a different point of view on things with a lower resolution, but we can have bigger pictures and more information on the surroundings of a specific area. But we also put them into Google Earth Engine to extract the NDVI and the other indices, remote sensing indices that I showed before. And the night lights, we get them from NOAA VIIRS product, and we extract night lights at 100-meter resolution, and also to download the rasters, we use Google Earth Engine to do the pre-processing. The linear model is a classic. It's a ridge regression, so you penalize the number of features for those that have a background in machine learning. And we make whenever you have a machine learning problem like this, we make sure that we evaluate the model correctly with always test sets that are different than the training sets. So that's the final prediction maps in the two locations. So we're predicting, I think, at 1 kilometer resolution, I think it's poverty as defined as the wealth index or something. So you can see that it's greener here than red here. So your intuition by looking at those